Ah. This is just the thing you hold on to. There's actually there's no pad on it. Like, oh, there it is. That's it's dumb. All right. So what we want to do is we want to assume that our function is continuously differentiable, and I want to prove to you that if we have that, we can construct the differential, and so prove it's differentiable in the real sense. So here we go. Theorem. Suppose f, a mapping from R2 to R2 is continuously differentiable at A equal to, let's say, A1, A2. Then f is differentiable at A, and df A of h is equal to, in fact, partial x of A times h1 plus partial f partial y at the point A of h2. So this is a specialized theorem. It's really all we need for complex. Okay? And so the proof is actually relatively simple. That's the kind of thing I shouldn't say before I start into a proof, because it's the kind of comment which will doom me to failure. But let's try. So P0 equals to A. And over here I'll put my so-called P1 equal to A1 plus H1 comma A2. And then up here I'll put my P2. And I'm just I'm following my notes a little bit, but I'm going to try to be much more explicit than the notes. The notes are very n-dimensional, the proof here. So I think it might kind of leave you a little bit wanting more. Well, I guess some of you might be happy with it. Others of you might be like, I haven't had linear algebra yet, so what are you doing, right? Fine. Now, what we're going to do is we're going to suppose all of this is inside. So we're assuming that the function's continuously differentiable at A. So if we study the topological aspect of this better, if you can't have continuity at a point without having the assumption of the theorem was that the derivatives exist near A, right? So let's assume that, h is small enough. I'm going to assume that h is small enough, if you will, that inside this, the partial f partial x and partial f partial y exist, all right? So we're working in the context where the partial derivatives exist. And more than that, they're continuous at A. And they're continuous. If they're continuous at A, they have to be continuous near A. All right, that's true. So then we look at line segments, yeah? Here. All right. And here. And just kind of focus our attention on there. Our goal is to understand how f of a plus h and f of a, the difference between those, can be approximated by the partial derivatives. So towards that end, let's look at f of a plus h minus f of a. Right? Well, we can rewrite that as f of, and I'll be explicit, a1 plus h1 comma a2 plus h2 minus f of, all right, so p1, f of p1 is a1 plus h1 comma a2, and then I'm going to add that back again. And then I'm going to subtract f of a. All right? Do you see why I'm allowed to do that? It's not really that. Not that, I mean, it's kind of silly. I just added 0, right? You guys see it? So far, so good? All right. Now, you guys tell me, looking at this right here, which of the inputs is fixed? Which of the inputs is changing? In my color coding, I really should do, is that the right color coding? I guess this is what I should have if I'm going to color code. Yeah? No? Like f of, oh wait a minute. I'm a dummy. Maybe I should just not color code. That one, oh man. This is why we can't have nice things. See here. That's this one. That's this one. All right, fine. Anyway, my point to you is, can you guys tell me what my point was? Right. Yeah, okay, so this guy here and this guy here, you say these are the same, right? And these are changing, right? If we look at these two. So what is that? What is that? If you take a function of several variables, and you hold one of the variables fixed, and you just change the other variable, that's a what? That's a partial derivative, right? Well, this is not a partial derivative. This is just a change in the function. But if we apply the mean value theorem to the partial derivative, there exists. See, we can write this as equal to partial f partial what? We're doing what? We're varying y, right? So it's partial f partial y. Where? Well, apparently at a1 plus h1, right? And then what? At some c2, which is where? Some c2, where c2 is an element of like, you know, a2 comma a2 plus h2. Now, admittedly, I am assuming that h1 and h2 are positive in the interests of not burying you in a pile of math legalese, right? And so the mean value theorem says what? It says the change in an interval can be approximated by the derivative at some point in the interval times the length of the interval. The length of the interval here in question is h2. That's how far you're going, h2. Right? And then by the mean value theorem, again, by mean value theorem, applied to the x partial derivative over there, we have partial f, partial x at the point, something, c1, and then a2 is fixed, yeah? And that all gets multiplied by h1 because that's the length of that interval. And here c1 is an element of a1 to a1 plus h1. All right? So this is the mean value theorem. How should we define our different? We got to propose an LH. I say I propose the LH be defined by partial f partial x at a times h1 plus partial f partial y at a times h2. Now, technically speaking, I should prove that that's a linear transformation, but that's a simple homework exercise that I have not assigned you, and I'm not going to, so relax. Like, that's better. Say that more, right? But this is a linear transformation, and I can prove to you that this satisfies the necessary Fréchet quotient. Let's see how. So let's look at what is f of a plus h minus f of a minus L sub h. What's that work out to? Oh, I have 3 minutes, so I'm going to have to do 2 steps at once here. So check it out. I take what's underlined in purple right here, right? This guy. And I'm going to group the things that have H1. And I'm going to group the things that have H2 because that's all that there is. In particular, we have partial f. I'm going to keep the partial f, partial x at C1A2 minus partial f, partial x at A of H1. Oh, sorry, all times H1. And then plus what? Partial f, partial y at, excuse me, A1 plus H1 comma C2 minus partial f, partial y at A times H, all times H2. You guys with me? Hold on a second. So I could call this thing, I can call this thing G1. Let's call this like, G1 of H. No, not G1 of H, just G1 of, well, yeah, fine, G1 of H. And I can call this one G2 of H, right? And what I have then, I say of H. Why do I say of H, guys? It's kind of sneaky. What's the H dependence there? Do you see where it comes in? Can somebody tell me where the H dependence is? Yeah, it's in the C, right? Not the A's, but the A is fixed here. Yeah. Oh, okay. Well, then excellent. So, how about we look at the modulus of this thing? Or if you like, I can put an H down here. Oh, I'm sorry. Well, it's not wrong, but I guess I should put this in our current discussion. So this is less than or equal to, the absolute value of G1 of H times, H1 over the length of H, right? Plus the absolute value of G2 of H times H2 over the absolute value of H. But my question to you is, what happens as H goes to 0 for G1 and G2, and why? What's the assumption? Continuously differentiable. That means as H goes to 0, what happens? What happens with C1 as H goes to 0? It goes to A1. What happens to C2 as H goes to 0? It goes to A2. What are you looking at? You're looking at the differences of the partial derivative close to the point. Those have to go to 0 because of the continuity of the partial derivatives. So by the continuity of the partial derivatives, G1 and G2 both go to 0. However, we have a squeeze theorem argument right here. See, because this goes to 0, this goes to 0, and these are what? Notice that we have I should put this here, right? H1 is less than H, right? So you can say this is less than or equal to the modulus of G1 of H plus the modulus of G2 of H. And I don't mean modulus, I mean absolute value here. And of course 0 is less than this, right? So then by the squeeze theorem, well, I guess less than or equal to is true, but by the squeeze theorem, then the limit's 0. And we have now proved that L of H so constructed is the differential Therefore, continuously differentiable implies differentiable. This is hidden in some kind of, horribly executed bad argument. All complex variables prove this in the context of complex variables in some sort of conniving, weird way, and you don't know what they're doing. And the truth of the matter is this is a theorem about real calculus, which has application to complex calculus, as we'll see next week. So, in any event, thanks guys.